If you want to understand how the internet actually works, not just the surface level stuff, but the actual plumbing that connects your gaming PC in Ohio to a server in Frankfurt, you have to understand IP addressing. And if you are studying for your CCNA or Network Plus certification, what we are about to cover isn't just a chapter in a book, it is the absolute foundation of your entire career as a network engineer. Welcome back. Today, we are doing the definitive deep dive into IPv4 addressing, the mathematics of subnetting, and the architectural magic that allows billions of devices to connect to the internet despite us mathematically running out of addresses years ago, NAT and PAT. I'm going to break this down in a way that moves past the dry textbook definitions. We are going to look at the logic, the binary math, and the packet-level architecture of network communication. We aren't just going to memorize numbers, we are going to learn how a router thinks. Whether you're an aspiring network engineer, a sysadmin, or a developer trying to figure out why your Docker container can't talk to the database, this is for you. Let's get into it. Let's start with the absolute basics, but we're going to look at them through an engineering lens. When you look at an IP address, like 192.168.1.5, you are seeing what we call dotted decimal notation. We write it that way because humans are terrible at memorizing strings of 32 ones and zeros. But to the router, the switch, and the network interface card, that address is purely binary. It is a stream of electrical pulses. High voltage for 1, low voltage for 0. IPv4 is a 32-bit address system. That means there are exactly 32 binary digits. We divide those 32 bits into 4 groups of 8. We call these groups octets. To understand subnetting later, you have to understand the binary value of an octet. In an 8-bit octet, each position represents a power of 2. Reading from left to right, the values are 128, 64, 32, 16, 8, 4, 2, and 1. If you turn all those bits on, meaning they are all ones, and you add 128 plus 64 plus 32 all the way down to 1, you get 255. If all the bits are off, or zeros, you get 0. This is why every section of an IP address is a number strictly between 0 and 255. You will never see an IP address like 192.168.1.300. It is mathematically impossible in an 8-bit octet. Let's look at the number 192. How does a computer see that? It looks at the first bit, the 128 position. It turns it on. It looks at the second bit, the 64 position. It turns it on. 128 plus 64 equals 192. The rest of the bits are zeros. So 192 is 11000000. Why does this matter? Because routers do not make decisions based on decimal numbers. They make forwarding decisions based on binary logic operations. If you don't grasp the binary, the concept of a subnet mask will always feel like magic. We want it to feel like engineering. Here is where students get tripped up. You cannot look at an IP address in isolation. An IP address by itself is meaningless. It's like giving someone a house number without a street name or a zip code. To understand where that device lives, the IP address must be paired with a subnet mask. The IP address tells us who and where. The subnet mask acts as the decoder ring that tells the device how to distinguish the who from the where. In networking terms, we call these the network portion and the host portion. The network portion is the street you live on. Everyone on that street shares the same street name. In a network, every device on the same local area network, or LAN, or broadcast domain must share the exact same network portion. The host portion is your specific house number. It must be unique. You can't have 2 houses with the exact same number on the same street, or the mailman, in this case the router, won't know where to deliver the packet. This causes an IP conflict, and usually the second device to connect gets kicked offline. So, how does the computer know which part of the 32 bits is the street and which part is the house? That is the sole job of the subnet mask. A subnet mask is also 32 bits. It works like a filter. Wherever you see a 1 in the subnet mask, that corresponding bit in the IP address is part of the network. Wherever you see a 0 in the subnet mask, that part is the host. When a router receives a packet, it performs a Boolean mathematical operation called a logical AND. It takes the IP address and ANDs it with the subnet mask. If you have a 1 and a 1, the result is 1. If you have a 1 and a 0, the result is 0. By doing this, the router strips away the host portion and is left with the network ID. This network ID is what the router looks for in its routing table to decide where to send the traffic. In the old days, we used classes. You'll hear about Class A, Class B, and Class C networks. Class A was for huge companies, utilizing the first octet for the network. Class C was for small homes, utilizing the first 3 octets. While you need to know this for the CCNA exam history questions, in the real world we use CIDR, classless interdomain routing. We represent this with slash notation. If you see /24, it means the first 24 bits of the mask are turned on, ones. Since there are 32 bits total, that leaves 8 bits for hosts. If you have 8 bits for hosts, you calculate the available addresses by taking 2 to the power of 8. That gives you 256. However, you can't use all of them. The very first address is the network ID, the name of the street. The very last address is the broadcast address, how you shout to everyone on the street at once. So a 24 network gives you 256 minus 2, or 254 usable IP addresses. Now let's tackle the beast, subnetting. This is the #1 reason people fail their CCNA on the first try, but it's actually just simple division. Subnetting is the act of taking one large network and slicing it into smaller, more manageable networks. Why do we do this? 2 reasons: performance and security. First, performance. Every device on a network broadcasts noise, ARP requests, discovery packets, Windows background chatter. If you have 10,000 devices on one flat network, the background noise would be so loud that legitimate traffic would slow to a crawl. We subnet to reduce the size of the broadcast domain. Second, security. You don't want the guest Wi-Fi users on the same network layer as your corporate finance servers. By subnetting, you force traffic to go through a router or firewall to get from one segment to another, giving you a choke point to apply security policies. In binary, we subnet by borrowing bits. Let's look at a scenario. You have a standard network, 192.168.1.0/24. You have one network with 254 hosts. But you need to separate your sales department from your engineering department. You need 2 networks. You take 1 bit from the host portion, the zeros, and give it to the network portion, the ones. Your mask changes from /24 to /25. By adding that 1 bit to the network side, you have created 2 subnets. 2 to the first equals 2. But because you used up a bit that was previously for hosts, your host count drops. You now have 7 bits for hosts. 2 to the 7 is 128. Minus your network ID and broadcast ID, you have 126 usable hosts per subnet. The rule of thumb is this: every time you borrow 1 bit, you double the number of subnets, but you cut the number of hosts per subnet in half. If you borrow 2 bits, you get 4 subnets, /26. If you borrow 3 bits, you get 8 subnets, /27. For the CCNA and for real-world engineering, you need to master the magic number or block size technique. You shouldn't need a calculator for this. Let's say you have a subnet mask of 255.255.255.192. We know 255 is all ones, but what is 192? 192 is the interesting octet. Take the total value of an octet, which is 256. 0 through 255 is 256 values. Subtract the interesting octet. 256 minus 192 equals 64. 64 is your magic number. This is your block size. This means your subnets count by 64. Subnet A starts at 0. Subnet B starts at 64. Subnet C starts at 128. Subnet D starts at 192. So if a device has the IP 192.168.1.70 with a /26 mask, which subnet is it in? Well, 70 is greater than 64 but less than 128, so it is in the 192.168.1.64 network. It seems daunting, but once you practice finding the magic number, you can calculate subnets in your head in seconds. Here is the problem with IPv4. It was designed in the 1980s. 32 bits gives us roughly 4.3 billion addresses. That sounds like a lot, but think about your house. You have a phone, a laptop, a smart TV, a smart fridge, maybe a smart light bulb. A single person might own 10 IP addresses. With 8 billion people on Earth, the math simply doesn't work. We technically ran out of public IPv4 addresses years ago. So why does the internet still work? Why didn't the web collapse? 2 reasons: private addressing and NAT. Engineers created a set of specific IP ranges defined in a document called RFC 1918. These are private IPs. You see them all the time. Class A private, 10.0.0.0 to 10.255.255.255, used for massive enterprise networks. Class B private, 172.16.0.0 to 172.31.255.255, used often in AWS and cloud VPCs. Class C private, 192.168.0.0 to 192.168.255.255, used in almost every home router. There is one more range you should know for troubleshooting: 169.254.x.x. This is a PIPA. If you see this address, it means your computer tried to ask for an IP via DHCP, nobody answered, so it assigned itself a panic address. It means your DHCP server is down. RFC 1918 addresses are non-routable on the public internet. If a core router at Google or your ISP sees a packet coming from 192.168.1.5, it immediately drops it. These addresses are free to use inside your home or business, but they cannot travel across the web. So, how do you watch YouTube if your laptop has a private IP that can't go on the internet? Enter NAT. NAT, or Network Address Translation, is the savior of IPv4. It lives on your router, that box your ISP gave you, or the fancy firewall you bought. Think of your router like the mailroom of a massive apartment complex. The apartment complex has one physical street address. That is your public IP. This is the address the ISP assigns to you. It is unique globally. Inside the building, every apartment has a number: apartment 101, 102, 103. These are your private IPs. When you send a request to Google, your computer creates a packet. Source IP 192.168.1.5, private. Destination IP 8.8.8. 8. Google. Your computer sends this packet to the router, the mailroom. The router looks at it and says, okay, 192.168.1.5 wants to talk to Google. I can't send this private address out there, it will get dropped. The router takes the packet, erases your private return address, and stamps its own public IP address on the envelope. Then it throws the packet onto the internet. Google receives it, thinks it came from the router, and sends the reply back to the router. But wait, how does the router know which apartment to send the reply to? If 10 people in the house are browsing the web, how does it know the Google search results go to your phone and not your brother's Xbox? This is where PAT comes in, Port Address Translation. This is also called NAT overload, and it is what 99% of home and small business networks use. When the router stamps its public IP on the outgoing packet, it adds a unique identifier called a source port. Think of this like a specific tracking number. It writes in its internal memory table, known as the NAT table, I sent a packet to Google using my public IP and port 55001. That conversation belongs to internal IP 192.168.1.5. I sent a different packet to Netflix using my public IP and port 55002. That conversation belongs to internal IP 192.168.1.10. When the reply comes back from Google, it is addressed to the router's public IP on port 55001. The router looks at its NAT table, sees the match, translates the destination back to 192.168.1.5, and forwards the data to your laptop. This happens in milliseconds, thousands of times per second. This allows a single public IP address to support hundreds or even thousands of devices inside a network. Without PAT, the Internet as we know it would have collapsed in the early 2000s. While PAT is the most common, as an engineer, you need to know the 3 distinct types of NAT because you will configure all of them. 1. Static NAT. This is a one-to-one mapping. You manually configure the router to say, public IP A always maps to private IP B. We use this for servers. If you have a web server in your office, you want it to always be accessible on the same public IP. In cloud computing like AWS or Azure, when you assign an elastic IP to a VM, you are configuring static NAT on the cloud gateway. 2. Dynamic NAT. This is a many-to-many mapping. You have a pool of public IPs and a group of private users. It's first come, first served. This is rare nowadays because public IPs are expensive, but you might see it in large campus networks. 3. PAT, NAT overload. As we discussed, this is many-to-one, many private IPs mapped to one single public IP using different ports. Let's apply this to a troubleshooting scenario. You're a junior network engineer. A user complains they can't access the file server. Check 1. IP and Subnet Mask. If the user is at 192.168.1.50/24 and the server is at 192.168.1.200/24, they are on the same street. They should be able to talk directly via layer 2 switching. If they can't, it's likely a bad cable, a VLAN mismatch on the switch, or a host firewall. Check 2. The gateway. But what if the user is at 192.168.1.50/24 and the server is at 192.168.5.200? Look at the third octet. The user is on network 1. The server is on network 5. They are on different streets. For them to talk, they need a default gateway. The default gateway is the router's IP address on that specific subnet. It's the door out of the room. If the user doesn't have a default gateway configured, or if it's configured wrong, their computer will shout, "Where is 192.168.5.200?" And nobody will answer because that address is on a different network. The computer needs to know to send that traffic to the gateway so the router can route it to the correct network. Check 3. NAT issues. If a user can browse the web, but a specific application isn't working, check the NAT type. Some legacy applications or voice-over IP phones hate PAT because PAT changes the port numbers. In those cases, you might need to configure port forwarding or one-to-one NAT to ensure the traffic gets through without the port number being altered. To recap, here is the hierarchy of knowledge you need to take away from this deep dive. 1. IPv4 addresses are 32-bit binary numbers. We read them as dotted decimals, but the router reads them as binary. 2. Subnet masks define the boundary between the network, the street, and the host using a logical AND operation. 3. Subnetting allows us to segment networks for security and efficiency by borrowing host bits to create more network bits. Remember the trade-off. More subnets means fewer hosts per subnet. 4. NAT and PAT are the necessary hacks that keep IPv4 alive. NAT translates private to public, and PAT uses source ports to track which specific device inside the network requested the data. Understanding this architecture is the difference between someone who just memorizes commands to pass an exam and a true engineer who can visualize the flow of data packets through the wire. If you are studying for your CCNA, I highly recommend opening up a subnetting calculator and doing the math by hand until it clicks. Don't rely on the tools, rely on your brain. Once you see the binary matrix behind the numbers, you will never look at an IP address the same way again. If you found this deep dive helpful, make sure to hit that like button so the YouTube algorithm, which runs on these exact IP protocols, knows to share this video with other engineers. Good luck with your studies, keep labbing every day, and I'll see you in the next one.